Welcome everyone to Einstein's Eyes. I'm your co-host Carl Rosen, oculoplastics, neuro-ophthalmology in Anchorage, Alaska. I'm here with my friend and co-host and former resident at Albert Einstein College of Medicine, ophthalmology residency, John Didkoff. John.
Hello, everybody. I'm John, and my practice is in northern New Jersey. Been there for over 30 years doing general ophthalmology, specializing in cornea. It's always nice to see Carl. We met before when we did our training at Albert Einstein, hence we came up with this name, Einstein's Eyes. So welcome.
We're going to talk about artificial intelligence and ophthalmology. I'm going to give you a brief primer on this, not too complicated. But let's start back 1956. It was a small artificial intelligence workshop at Dartmouth College. It was run by John McCarthy, Marvin Minsky, Claude Shannon, and Nathan Rochester. Gave the field its name. Now, artificial intelligence, you could trace it back thousands of years, but really let's start in the 1950s. A little earlier than that was Alan Turing. And Alan reframed the question in 1950. The Turing test, which was coined by Alan Turing, a mathematical genius in the early 50s, before the Dartmouth College workshop, essentially said, can machines think? And the Turing test is a test of machines' ability to exhibit intelligent behavior, indistinguishable from that of a human. Let's jump to 2017. There was a seminal paper called Attention is All You Need. It was written by Ashish Vaswani, Noam Shazir, and a number of others. This paper introduced attention, and as I mentioned, the attention is all you need came from the Beatles song, Love is All You Need, to the modern era of artificial intelligence. Helped us understand that you needed to pay attention to the most relevant parts of a sentence. And these sentences or these words were tokenized, or they were parsed up and segmented into a mathematical number, a matrices. And this allowed for large language and vision language models by something called a transformer. You don't really need to understand this, the schematic of the transformer highlighted in this paper, and this was revolutionary. It went from something called BERT to something called GPT, which is what we know today as ChatGPT and natural language processing, and has led to modern artificial intelligence, which we all use. What's important here is understanding the embedding process and the encoding process. The math involved in artificial intelligence starts with tokens. We chop sentences into tokens, words or subwords, we break them up, and we do something called embedding. Embedding takes these tokens or audio file or an image file, and it creates a matrices with various types of chips. Now, the chips can get complicated. NVIDIA has these chips called H100, which are the most advanced, and the Trump administration is preventing China from acquiring these because of the competition. America wants to stay ahead. These chips are called GPU chips, are versatile parallel processors, and they're good for a broad range of tasks available across cloud providers. There are other types of chips called TPUs, which are more designed for large-scale matrix operations and deep learning. Most of us are really concerned with the GPUs. GPUs are responsible for embedding, and the embedding process takes each token as a long row, mostly zeros, and we multiply it by embedding matrix that the model learns. This in turn turns each token into a short, dense vector or a list of numbers that captures meaning. Now, similar meanings live close together. So optic, from optic nerve, lives near retina, live near meibomian glands, and the model measures closeness. This is also called the cosine similarity to group related terms. And attention layers then look across all tokens to decide which vectors matters most to predict the next token. When a large language model or LLM answers a question that you put in the context window, it's not recalling facts like a person would recall facts. It's predicting the next most likely token using those vectors and attention. And that's what people have to get straight. We are running towards something called AGI, Artificial General Intelligence, and hopefully ASI, Artificial Superintelligence. And let's talk about the major players. On the general purpose side, you have Google DeepMind, you have OpenAI, ChatGPT, which was revolutionary. 700 million users a week. Anthropic, Microsoft, Meta, NVIDIA, and XAI with Grok. Elon Musk recently has said that AGI will be attained with Grok 5. We'll see. That could be coming up in the next few months. They're pushing the frontier models, and the frontier models are these ChatGPT 5, Opus from Claude, Sonnet from Claude, Llama from Meta, etc. And they're using compute to run them. And compute is very important. And again, that's where the chips come in. The more compute, the faster you can train a model. And that's where these data centers come in. XAI is using a facility in Memphis, Tennessee. They have a very large data center with over 200,000 GPUs. That's their compute energy behind the training model. In ophthalmology, the players in this field, Digital Diagnostics, the makers of IDx-DR, have the first autonomous AI to get FDA authorization for diabetic retinopathy. Another player is EyeArt, also FDA cleared, and now validated across multiple camera types. AEYE Health also earned clearance with a handheld pathway, and they're bringing screening closer where patients are. Now, again, you need a big camera, they're heavy, it's not super simple, it's not on a mobile device. But why this matters in eye care and how we actually use it is where we're going to go. The US faces a growing shortage. It's a supply-demand curve. The United States faces a growing supply-demand mismatch. There's a shortage of ophthalmologists. There's only 16,800 ophthalmologists in the US. This number is flat or declining. There's only about 460 to 490 new ophthalmology residents per year. Over 2.4 million visits to an emergency room that's ophthalmic related. That's a lot of visits per day. It's over 6,000 visits per day. Many of these patients are not seen by an ophthalmologist because the EMTALA system, the Emergency Medical Treatment and Labor Act, can't find ophthalmologists to take emergency call. So we have a shortage. It's very expensive. It's difficult to get an appointment with an ophthalmologist. It can take well over a month. It's just not fun to go to an emergency room and wait around and then not be seen by an ophthalmologist, but be seen by an emergency room doctor who doesn't have the same fund of knowledge. And it's all very expensive. My supposition, my theory is that AI can help support clinicians, even patients at home, by training an ophthalmology-specific model to capture, analyze, report, and then integrate this into an AI application that can assist the clinician as long as the diagnostic accuracy is exceedingly high, over 90%. We have to keep the clinician in the loop. We can consider this an educational tool. If we had an artificial intelligence ophthalmology-specific model, we can use this, again, to supplement the existing shortage we're faced with. Now, John, what's your view? What do you think?
One is patient, direct to patient. So, I mean, there are patients that have a problem at home, and some of them already, they go on Google and they can look things up and they know they have a sty. They can watch videos like we have on YouTube. And the advancement in AI that's happening so quickly will really direct them a lot quicker and easier than having to search themselves. We already see, the rapid progression in AI and the ease of use. So I think that's going to be one way. That's what I see. The second way, I think, is like you mentioned in the emergency room. So not even just emergency room, but you have general clinicians. You have people go to their medical doctor, they go to their pediatrician, they go to their nurse practitioner, their PA, their primary care doctor, whoever that is, or primary care person, because now it's not just going to be doctors, and they're going to have access to AI. So that's going to direct them like, hey, I can handle this, or do I need to really refer them to an ophthalmologist? So that's going to cut down on the amount of visits that need ophthalmology. And then the third is in an ophthalmology practice like myself, where I have technicians, I have receptionists, I have optometrists, and we even have general ophthalmologists of specialists. So we have a hierarchy of different type of care. And I think with AI, ultimately, I think this will be expedited so that you don't need as much staff. That's, I think, the hope and the goal, as long as it's being done correctly and efficiently and well. So I think those are the three that I see. What do you think about that?
I think we'll create another video to really explain how this application would work, what the workflow would look like. But in a nutshell, I think we need to do is create a mobile as well as a desktop device that can capture images in a multimodal way, audio, text, images. You import from, say, an OCT, a visual field, a CT scan, an MRI, or just an iPhone camera for external images, or a fundus camera for diabetic retinopathy, glaucoma, macular degeneration. These are the big three. That
As
data.
you know, one thing I would point out is as a doctor that's had 30 years of practice, 30 years of being in practice, I guess practicing, a lot of it is history. It's not always visual. I mean, even though ophthalmology, it seems like it's really visual, and that's why AI is going to be right there. But AI is very good at eliciting a history. It's going to know how to do that. It's going to know the right question to ask and the right patterns that we do as doctors. I walk into a room, when I talk to a patient, I would say at least 90% of the time, I know what I'm going to see before I look. So I think that's going to be the key. I think it's going to be intertwined with history taking, but AI can do that.
Right.
AI can ask questions. AI can definitely drive patients to a certain, or, like they can ask the right questions and then can visualize it. Basically ask those questions and then say, now put your eyeball here or put your face here. And I think it can do those things.
Right. As long as you take a model, it's got to be small, because otherwise the model gets lost in all the jargon and the text. Train it well with proper images and text, and make it diagnostically accurate so that it doesn't hallucinate and it gives you the correct diagnoses and leads you in the right direction. It helps the clinician or the patient with an assessment and a treatment plan, or at least a triage method.
Right, that's the key.
This thing is happening, and I think it's down the road. But like I said, I'd like to talk about in a separate video what this workflow would look like. I think it's really going to be fascinating. And again, the supply-demand curve needs to change. The cost needs to change. But thanks everybody for being here. John, great to see you. And we're going to talk about this some more. I'll see you on the next one. Thanks, John.
Thanks.
Thank you.